Okay, pre-cal 11, here we go. Let's get after it. Video number 5. We are going to work on simplifying radicals. And who doesn't like life a little bit more simpler? So let's look at some reminder pieces here. Remember that radicals can be written as fractioned exponents. So root 2 is the same as saying 2 to the 1/2. Fourth root of x is x to the 1/4. Remember your flower power, because here we get x to the root is 4. Flower is 3, which is our power. That's going to come in handy when we start simplifying these things. Now, there are some pretty important relationships for you to consider. The first one is this. If you have um, a base here to a power and it is under the same root, those cancel each other off, right? So the square root of 4 squared is 4. The fourth root of 2 to the 4 is 2. They cancel each other out. Now, what we need to consider, though, is our a value positive? Because if a is negative, there we could have a little bit of an issue, right? If a is negative, so if we have -2 squared and then square rooted, well, in this case, the solution is 2 because we're squaring -2 in brackets. And this is a few videos back, I talked about the importance of brackets or no brackets, right? Because this would translate to this, which would then translate to that. Now, that is given the distinction, again, remember that this is already written under a square root sign. And this is where things can get a little finicky and a little frustrating when you're dealing with negatives. So just take it as a case-by-case scenario. So yeah, take it one case at a time and see if it makes sense. Often you will see restrictions. So in this case, a restriction is given that a is positive. So it removes this scenario from our thought process. So look for your restrictions first. The next important relationship is this one. So here again, we're given a restriction that both a and b are positive numbers. So we're assuming that they are both positive, okay? Now, this is a really important relationship because it says that if you have two things that multiply by each other underneath the radical, they can be written as separate radicals multiplying together. And you're going to see this in the addition section because I've highlighted how we can really simplify our fractions before, or our radicals, sorry, before we add them together. So here's an example in real play. Let's say we had the square root of 32. Well, you can break this up however you want. And you can think about breaking it up with respect to how you would break 32 up. Well, 32 is 4 times 8. 32 is also 2 times 16. So let's say, so you could say, well, the square root of 32 is actually the same as the square root of 4 times the square root of 8. Or the square root of 32 is equal to the square root of 16 times the square root of 2. And what this does is this allows us to simplify in a much easier way, because if we can find a perfect square as a factor, it will simplify out. Because here, what's the square root of 4? Well, it's just 2. So I have 2 times the square root of 8. Now below here, I'm even further because this is 4 times root 2. Now you would think the answers should be the same, and they are. It's because we're not actually done with this one. Because root 8 can be written as root 4 times root 2, and now you have 2 times root 2, which, times root 2, which gets us back to 4 root 2. So by identifying a perfect square factor underneath a root, we can break it into two different root statements. So let's do one more. Simple enough here. Imagine if I had the square root of 200. Well, guess what? That's the square root of 100 times the square root of 2, which is 10 times the square root of 2. So knowing your perfect squares is going to become really helpful in this scenario. Again, this is a fantastic relationship. Very good to know because it'll help us simplify quickly. The next one is similar to that, the one we just did, but if you have two numbers underneath one radical, you can again split them up. Now, why does this come in handy? And again, here we have two stipulations, and these stipulations are important. A is a positive number, but can be 0, but you can see here B is not allowed to be 0 because we can't have 0 in the denominator. So look for these restrictions on the statement. Now, what do I mean by this? I mean, okay, so imagine we had the square root of 4 over 9. Well, that's the same as the square root of 4 over the square root of 9, which you can then simplify to 2 over 3. Or, here's where it would be a little bit more helpful, just for notation-wise. Imagine you had the square root of 3 over 16. Well, that's the square root of 3, square root of 3 over the square root of 16. Now, the square root of 3 can't be simplified, but the square root of 16 can, and we end up there. Now, that is what we call a rational expression. It wouldn't be rational if we kept an irrational number in the denominator, but you'll see that in our multiplication video. So understanding this relationship here is also going to be incredibly helpful as we move through levels of complexity. So let's do a few examples. So we're looking for perfect square factors, and here we have 20. Well, I know that 20 is 4 times 5, and 4 is a perfect square. Awesome. 2 root 5. Done. Now, I will quickly just show you one other way to consider it is every time you see two identical factors underneath, they come out. So if you were to break 20 down, 20 is 2 times 2 times 5. So if it's a square root, we're looking for two identical factors, 1, 2. They would join up and combine on the outside. So it's exactly the same as what's happening here. Personally, I preferred this, but a lot of people like this. So just be aware of both, okay? Let's do a couple more. So now here we go. Cube root. So for a cube root, we need three identical factors. Now for me, I know my perfect cubes are 1, 8, 27, 64, 125. And I identify, well, wait a minute, 24 is 8 times 3, and 8's a perfect cube. So I'm going to go, okay, well, that's the cube root of 8 times the cube root of 3. This will simplify, so now I have 2 times the cube root of 3. Now again, if you were to do it the other way, and you were to break 24 down into its primes, or close to, we'd have 2 times 12, which is 2 times 6, which is 2 times 3. You could say, okay, well, the cube root of 24 is the same as 2 times 2 times 2 times 3. And since our index now is a cube, we're looking for three identical factors. So 3 of them would combine and come out as 1. Same process, just looking at it in a different way. Now, here we go. We got a bigger one. So looking at this, I don't necessarily know exactly what perfect square factors are of 180. So I'm going to show you how to break this down and do it that way. So if you get 180, well, love numbers that end in 0, 18 times 10. And 10 is 2 times 5, 18 is 2 times 9. Now I'm actually going to stop there because I notice I have two 2's, which are identical, and I have 9, which is a perfect square. So I can write this out as 2 times 2 times 9 times 5. Those are my numbers. And then I'm actually going to look at this and say, well, x to the 6 is just x squared times x squared times x squared. Remember our exponent laws? And then y cubed is y squared times y. Now, why do I do that? Because perfect square factors, well, here I have two 2's, which is the same as a 4. So that's going to come out as a 2. The square root of 9 is 3. The square root of x squared is x. The square root of x squared is x. The square root of x squared is x. The square root of y squared is y. Nothing else can come out. So what's left on the inside? A 5 and a y. So what we end up with is 6x cubed y times the square root of 5y. Look at that a different way. If we look at what came out, a 6 came out. So 180 divided by 36 is 5. So technically, the square root of 180 could be written as the square root of 36 times the square root of 5 times the square root of, now, x to the 6, is x cubed squared, right? So the square root of x cubed squared times the square root of y squared times the square root of y. Now, 6 x cubed y, and then what was left? 5y. Same thing, just a different way to look at it. These will piss you off for a little bit, but they'll grow on you. You'll start to get the hang of them. Let's look at some more. Okay, now this is an instance where we have a cube root. So remember, we have the cube root of x to the 12 over the cube root of 64. Now, 64 is a perfect cube, 4 times 4 times 4, so done. And x to the 12, well, think about what x to the 12 is. It's x to the 4 times x to the 4 times x to the 4. And that is an identical factor 3 times, so that's coming out perfect cube x to the 4. Variables with exponents are definitely going to be a little bit trickier than numbers, but just get to know the relationship. Yes, I have that, and it's x to the power 4, but I have it 3 times, and I'm under a cube root, so I need 3 identical factors. As soon as I have 3, they come out as 1 right there. Okay, now the opposite, making an entire radical. So an entire radical is when we send the number back in. So there's 2 ways to really think about this, and it's just the reverse of what we did. If you're given this to start with, in order to multiply the 3 back in, it has to be a root. So basically you're saying, okay, well, what is the square root of 3 with respect to a number under the root? And it was the square root of 9 is 3. So 9 times 5 gets us back to root 45. So that's one way. The other way is, if you think about those identical factors, in order for 3 to come out, it must have had 2 on the inside. So when you put it back on the inside, you just have to put 2 on the inside. And again, we get root 45. Now, on the question here on the right, you'll notice we have a stipulation. And the stipulation is given x is positive, because if x was negative, we'd have a problem in here because we'd have negative under a square root and it wouldn't work. So that's why they put that stipulation in there. Now, on that same note, there's a negative out front here, which means that negative cannot go back into the root. It's not, you can't assume negative 4 times negative 4, because when it came out, you didn't know that it was a negative 4, right? If you had, what I mean by that is if you're given the original statement as root 16 and then you're given the answer, you don't know there was negative 4 times negative 4. So if you have an even indexed root, that negative has to stay outside. It cannot go back inside. That negative just has to stay out here. And then what would have come out? Well, we have 4 times 4 then on the inside, and x squared times x squared back on the inside, because that's how they made their way out. There was 2 of them to begin with. And then we have the 5, and we have the x cubed. And then we just simplify and multiply that all together. So now 4 times 4 is 16. 16 times 5 is 80. So we have negative outside, and then 80 x to the 7. So be careful with negatives if you have an even indexed root. See here, you're given a stipulation, but only for the question itself, because we have a cube root, so it doesn't actually matter. Now, what the cube root means is, however many we had on the outside, that's how many have to go back to the inside. So if you have a 2 on the outside, it means there must have been 3 on the inside. You have an x on the outside, means you must have had 3 on the inside. Same with the y. And then you're left inside with a 4, an x squared, and a y cubed. Now, if you're a keen observer, you'll be like, well, why is there a y cubed out here if it could have come out? Good point. It could have come out, but it wasn't when it was given to you. So just be aware of working with what you have. So now when we multiply all of this back together, you get 2 times 2 times 2, which is 8, times 4, so 32. And then you have x cubed times x squared, which is x to the 5, and then y to the 6, and it is a cube root. A couple more here. So, how do you make an entire radical when it is a fraction? But just remember that a fraction like this is the same as a fraction like this. So that 5 on the bottom, it just means when it goes back into our radical, it's going in the denominator. So it's a cube root again. So we're going to have 3 5s in the bottom. And then a 3 was out, so we're putting 3 3s back in. An x squared, so we're going to have to put x squared 3 times, which is the same as x to the 6. And then a y, so we had a y cubed. And what are we left with on the inside? Well, we already have a 2, an x, and a y squared. And now we just combine everything together. And it's all going to be under the radicals. So 125 on the bottom. 3 times 3 times 3 is 27. 27 times 2 is 54. And then x to the 7, y to the 5. Because yes, this is, sorry, cube root again. And this is a perfect cube on the bottom, which is why in our question, it was the only number in our denominator. Remember, you can think of this as over 1 because the 5 goes back in on the bottom. Last one. Now here we have a 5th root, but we also have a subtle difference because now it's an odd index, which means this negative can go back in because the negative comes out, right? Because in an odd index, the negative actually can transverse both ways. Because you know that if you have negative 2 to the power of 5, well, the answer is just negative 2. It's not plus or minus. So in this case, you don't have to write the negative every time either. You just know it's going to be negative on the inside. And then you're bringing in 2, but 5 times, so 2 to the 5. You're bringing in an x, but 5 times, x to the 5. And then you had a 4 and you had an x on the inside. So in this case, you're actually left with negative 2 to the 5 is 32. 32 times 4 is 128. So negative 128, x to the 6. And in this case, that negative by itself there, don't even think of it as attached to the 128. Think of it as a negative 1, because negative 1 to the 5 is still negative 1. So that means it just comes in and out as a negative 1. And don't consider it as being attached to that 2. It'll just make life a little less confusing. Negative 1s, so the negative in front of a number, can move in and out of a cube or a fifth or any odd indexed root. So a lot happening in here. The negatives can really start to throw you for a loop, but just get used to at least comfortably simplifying. So breaking things down by finding perfect squares, perfect cubes, perfect fourths, or breaking it down into factors and finding the adequate number that you need. Okay, thank you so much, and I will see you next time.